Detour. I asked you 4 times
You sold
why
us.
it says this, and then you said just ignore it. 4 times. This is your fault. He deserves a -7.
Oh, he tanked it.
He did?
Yeah, so did
Oh,
I,
yeah.
because I...
But I did all of them as the same thing. Do I need to change all of them?
Yes. Well, why would you
Come on,
say
give him
it
some
would?
points.
But then how
Yeah, maybe half.
Yeah, they did
Zero's
it right.
off means that there's nothing flowing through
But
it.
that's the highest, that's technically the
Yeah,
lowest
technically,
number.
that's exactly. The logic behind the system. Y'all just need to
No,
read the
zero means
instructions.
that there's nothing, it's off, boom.
Zero is the
There's not like a-
One is the brightest. I,
if it's off.
no, in all the years I've done this, I've never, ever had kids screwed up. Never.
It was Detour's fault.
That'd be your
He was like,
The
you
first.
said that you said to do it as highest number's the
I
brightest.
thought they said 13 out of 30.
If you want to resequence them and hand it in, I'll regrade it.
Alright.
What is this so loose?
Oh my god.
Okay, anyway.
What a generous.
So here's what we have today. So no matter, so right now we've got this kind of assembly scheduled for Wednesday during 4th block.
What?
So no matter, that's not going to impact tomorrow. Okay, the only thing it might impact is whether we go to the assembly on Wednesday and take the test on Friday, or we skip the assembly and do that on Wednesday.
What's this?
I thought, from what I had read from the administration, it's kind of expected that we go, but now I've talked to some other teachers, says that's kind of optional.
What is it?
Yeah, what's it for?
It's like a sad presentation, something, I don't know.
Oh.
I really didn't pay that much attention to it because I thought we had to go.
Students
So
against
let me sort through all of that. That's not going to impact today, and it's not going to impact tomorrow. Okay?
Okay.
That's going to happen. The only question is whether we have the test on Wednesday or we have the test on Thursday. I will obviously let you know tomorrow. But it's not going to make any difference in terms of what we're going to do today. All right. So when you look at capacitors, okay? So on yonder equation sheet, first off, you have to understand what capacitors do in a circuit. So even when you look at the symbols, the symbol for a battery is like a long and a short, okay? Symbol for a capacitor are 2 equal length lines. So just like a battery, you have to charge it. The same thing is going to happen with a capacitor. You have to have some source of energy to build up the charge. So when you have a capacitor, and I'll go back and I'll show you all this in some circuits in just a second. So when you have an uncharged capacitor, Mother Nature is in the state of equilibrium. If you measure the voltage across it, your voltage is going to read 0. There's no potential. Nothing's going to happen. So if you go with an analogy of a river, okay, so if you go with an analogy of river, that's like there's no water stored behind the dam, okay, it has no potential. So if you want to store water behind it, obviously you have to have river flowing into it, you shut the gates, boom, you begin to build up this water that's behind it. So the same thing is going to happen with capacitor. So you're going to put energy into it. So what we're going to do, for example, I'm going to hook it up to a battery. So that battery is going to have that electricity flow through it. Capacitors, like LED lights, have a direction, okay? And when you look at a capacitor, you'll see, and I'll show you this, is going to have an arrow on it. And that's the traditional flow of the current, not the electrons, okay? The flow of the traditional idea of a current, going from positive to the negative. So what happens is that capacitors, and this is what we talked about on that problem that I just gave back. So initially, when you deal with capacitors, when you first put it into a system, that electricity just flows through. It's just like it's not even there. So, and you'll see this a couple of different ways. So as that capacitor has that energy flowing through it, eventually what's going to happen is that it's just like you've shut off all of the water flowing through the river, okay? And no water is going to be allowed through it. That's when it's going to have its maximum potential energy. So when you look at the equations for capacitors, there's like 5 of them. Q delta V, which is 1/2 C times delta V squared. And then you have capacitors in parallel. And then
Is that a little Q? Or a big Q?
hold on.
The top one. Or does it matter? That's a Q.
That's a lot of equations.
Is that a C?
Okay,
Oh, there it is.
so here's how like all of these fit together. First off, just like a dam stores gravitational potential energy, you can store potential energy behind a capacitor. Okay, that's the whole point of it. So there's 2 different ways that you can look at the potential energy stored in a capacitor. One is that it's Q delta V. So if you look at the units, okay, hey, that's voltage. That's joules per coulomb. Multiply that by your charge, boom, those cancels out, you get joules. Okay, so that's what any potential unit is going to be measured in joules. So then, when you look at the other way that you can do this is this capacitance, and this is your voltage squared. So to calculate your capacitance, and this is where this all kind of fits together. So one idea that you can look at in terms of capacitance, and it's the same kind of equation, but it's really not the same. So if you look at this, this is your standard way to calculate capacitance. This is this Greek letter K, and it's technically the Greek letter Tau, and that changes dependent upon the type of capacitor, but literally the only time I've ever seen this done in terms of the AP exam, that always equals 1. So I've never seen them have anything other than a value of 1. So basically ignore that. So you have this epsilon naught, which is vacuum permittivity constant. A is the surface area of the capacitance, and D is the distance between the plates. So if you want to build a big capacitor, you have a big area, and then you have a very small distance between the plates. Louis?
So is epsilon not voltage?
No, epsilon naught is this permittivity constant is like 8.99 whatever times 10 to the negative
So
12.
epsilon is voltage?
So no, epsilon naught. Okay. What's up, Mags?
Can you fill out this reference letter for me?
You're kidding
It's not
me.
actual, so you get the right use of the rank me.
Yes. Who do I give it back, and when's my deadline?
I'll come get it from you.
When's my deadline? Give me a deadline. I'm going to put it off till the 4th of July.
I'll come get it this week. Like Wednesday.
Okay.
Okay, thank you.
All right. Take a Post-it note and put a deadline of Wednesday morning,
Okay.
or I'll completely forget it. Love you to death, but I know me, and I'm going to forget. Okay. Okay. All right. So this, when you're talking voltage, that's just like a fancy E. This is epsilon naught, which is that permittivity constant.
Okay, all right.
Okay.
Gotcha. So it's completely different things?
Yes.
Wait.
And just like L's can have different things. When you see that not value on the end of it, so let me see your yellow sheet.
This one?
Yeah.
Wait, what is that again?
So you don't know.
Okay.
C equals
So
what?
this
What even is
epsilon
that?
naught,
K epsilon naught.
this vacuum permittivity constant, 8.55 times 10 to the negative 12 coulomb squared newtons meter squared.
So I'm supposed to use that?
If, depending upon what you're given, so if you know, if they gave you the area of the plates and the distance, okay, then multiply that by this epsilon naught, and that's how you're going to get your capacitance. okay? Louis,
If the K was to change, what would kind of, like, why would that change? And
what that changes in, like, K is a whole number, typically it's like 1, 2, 3, or 4.
Yeah.
So it's just a direct relationship, so as you increase the value of K, or that cal value, that just increases your capacitance.
like what is Cal though?
It's just it's a numeric value based upon the material that the capacitor is built out of.
Gotcha.
It's kind of like a 6-volt battery versus a 12-volt battery, okay? But it's just a numeric value, and it's always 1 unless it's something bigger. Okay, so you just generally ignore it.
Wait, the 8.85 one we use?
Yes.
Okay.
Now, here's the other thing, and I'll show you this in just a second. So when you have capacitors in series versus capacitors that are in parallel, this is like the opposite of what happens with resistors. So if you have capacitors that are in parallel, so let's say you have a battery hooked up, okay, and then you have 2 parallel capacitors. The capacitors are measured in units called farads, okay, and typically it's very small. Like, for example, a 1 farad capacitor is huge, okay, relatively speaking. Typically, they're like 5 microfarads or something like that. So let's say that you have 5 and 5 as your capacitors that are in parallel. So if they're in parallel, then you just add them. And this is like the opposite of what happens with resistors or light bulbs. So if light bulbs are in parallel or resistors are in parallel, you add the inverses. With capacitors, you just add them straight up, okay? So that's what you have to think through. So resistors or light bulbs are in parallel, you add the inverses. Capacitors that are in parallel, you just add them straight up. But then if you have 2 capacitors that are in series, then you add the inverses of them, okay?
Is there a reason for that, or is it just because?
It's just because.
Okay.
It's just because. Okay, that's the basic idea. So shut that down, bring that camera, let's go to the back. This is much more now complicated than I thought it was
I
this
did not
morning.
do that.
So I've got to sort through some information. Okay, so here's what I've got. So it looks horribly complicated, but I've got a battery, a switch, an LED light, a 10 ohm resistor, a capacitor, and this is a 100 microfarad capacitor. And notice that that has an arrow on it, okay, which is indicating which direction the current needs to flow. So if you look on this, I've got the positive terminal of my battery over here. And so what's happening is that this, by the old school definition of how current goes, so it's going to be leaving here, flowing through the switch, going to the bulb, capacitor, boom, the resistor. That's the direction that it's going to go. So what I'm initially going to do, and then I've got a voltmeter hooked up, okay? So what I want you to do is focus on the LED light, okay? So focus on what's going to happen with that. So I'm going to close this, okay? So when I do this, notice that that LED light initially got very, very bright. And then it went out. Why?
Capacitor filled up.
Yeah, the capacitor got fully charged, right? Okay?
That was cool.
So this is why, and it doesn't take very long. So in the problems, it will tell you a long time. A long time is a relative amount of time, okay? So right now what's happened is that if you look at this in terms of a dam, okay? So we charged this thing up. Initially, that was allowing electricity to flow through it. Once that capacitor got fully charged, it in effect shut off the gates to the river. This light went out. But now, what's happening is that this is holding a charge. So if I hook this up to a voltmeter, okay, and I measure that voltage across that capacitor, okay, so this is reading about 7 volts, okay, which is oddly enough the exact same voltage as the battery is. So what's happened is that voltage across here is the exact same as it is across that capacitor. So it took that energy and now that's going to be stored. Now, if I disconnect this, Okay? So the beauty of capacitors is that they act like a reservoir. So now, what I'm going to do, I'm going to hook this up. Okay, so now I'm going to hook this up here. Okay? And now, what's going to happen is that now I'm going to close this switch. Oh, hold on.
Uh-oh, something wrong.
I might have already lost so much. Hold on. I got wires coming off there. This is what I hate about circuits. Dink. Disconnected that. Let's go over here. Let's go like this. And I might have already lost too much of it to light up. Okay, let me charge that back up. Hold on. We're good. We'll get there. Okay. So we're charging it up. Okay. Do it real quickly. Disconnect that. When in doubt, reverse the polarity LED light.
Switch.
Charged up. There we go. There it went. Okay.
Right.
So here's what happened. So I charged this up. That light came on very, very quickly. I charged up my capacitor. I shut this off. I closed this switch. Okay, so at that point I offloaded that electricity that was stored in that capacitor. It went to that light. Okay, so now let's start to make some predictions.
Wait, so
I have
what
a
happens?
So
Um,
hold on. Let me think through getting this hooked back up,
okay.
and then I'll take your question.
I also have a question.
Hold on.
Oh,
So we just both.
Okay, so this is not part of the circuit. Okay, so I'm going to close this switch. The voltmeter basically now is reading 0. So when I close this switch, what should happen to the reading on the voltmeter?
Wait, what is it?
So I'm going to close the switch. This is not part of it. Okay,
Okay.
not part of the system. So I'm going to close this switch. What should happen to the reading on the voltmeter?
should go up.
It should go up, right?
Yeah.
So I do this.
Yep.
Okay.
But it should slowly.
It spikes because that build up that electricity.
Yeah.
Now, I'm going to open this, okay? Then I'm going to close this switch.
Okay.
So what should happen to the reading on the voltmeter?
Slowly. Yeah.
It should go down because now
You discharge. Light.
I discharged that electricity that was stored in that capacitor. It went to the light. This is going to drop back down to 0. Okay.
Wait, did that stay the same, like when you had both of them up?
Yeah, so let me open this back up. Okay. So I closed this. So that spiked. So the voltage across that capacitor is the exact same as the voltage is across here.
Oh.
Okay? Got that idea?
Yes.
Okay. So
Yeah, but like when you brought that up,
when I close
did it
this,
stay the same?
yeah, but what's going to happen is that that's slowly going to discharge. So this is why this voltage is going down. But if I close this, then I offload that energy very quickly. And that's why that drops so fast. Okay?
Oh, so it never fully charges.
No,
what?
but when it's it's just going to discharge over a period of time.
Okay.
And so how you rate capacitors is basically, there's a couple of things. The biggest one is the time factor. How long does it take for that capacitor to offload that energy? So it's like if you make the dam analogy, do you open up the gates a little bit, or do you open up the gates all at once and let that electricity flow out very, very rapidly? And so this has a very, very rapid discharge. So like if you look on your phone, like you're at night and you need a flash, okay? You need a very, very rapid discharge of that energy to make that bulb flash very, very brightly. Okay,
I had another question.
Okay. Yes, ma'am.
So, like, when this was down, you know, and then
Yeah.
you fully charged the capacitor, is there still current going through?
No. Once that's fully closed, there might be a little bit bleeding by, but basically,
So the electrons aren't moving through at all?
no.
Nothing?
There's a little bit, which is why that LED light still kind of glows a little bit, but it's in theory.
But, like, yeah, in theory, like, when we
In theory,
think
that
about
should
problems,
completely shut that off.
So nothing will happen, it's just, like, nothing's going on? It'll,
No.
like, be
It's
as
just,
if
it's
there's
just
no...
like everything's disconnected.
Okay.
Okay? Okay, now, I'm going to close this switch, okay? But I'm going to have this switch closed as well. Okay? So this is now part of the circuit. So I'm going to close this switch. The question being is what's going to happen to this light and what's going to happen to that light?
Both
gonna light up.
Why are they both going to light up?
Because there's energy going in and out of the capacitor, so
Yeah.
it just works as like a wire.
Okay? So when I close this,
Let's go.
You're correct.
okay?
Baby Paul.
So basically what's happening is that but I did get a little bit of a spike in the voltage, okay? So it basically, this started to build up electricity, and it's going to store some voltage. Now, but basically Mother Nature goes, this is going to take the path of least resistance. So once that builds up enough charge, then it basically says, hey, I'm going to divert that over there. Now, if I open this switch, then what should happen?
It
Yeah.
charges.
What's going to happen to that voltage?
Go down. Go down.
Doesn't it go up?
Oh.
Wait, no,
And
it
then
goes
it
up,
turns
goes up,
off.
goes up, yeah,
Goes
goes
Goes up and turns off after it's
Yeah, it goes
charged.
up. Yep, goes up. Yeah, it goes up.
So I close this,
Open it.
Spikes.
Close it.
or open it, I should say. So now, notice what happened to this one.
Went off.
It went out. Why?
Because the capacitor
Just
is
pass
The
it.
capacitor is now fully charged.
There's
Yeah.
no other place to go.
Yes, it's storing that voltage, so that is now effectively acted as a dam. I close this, now what's going to happen?
Gonna go down a little?
Both of them are gonna line
Yeah,
up.
so they
Both of them
yeah.
will light up, and that voltage goes
down.
down.
Oh, okay.
Wait, how come it goes down? Because it's the same battery.
But, so what's happening is that it's going to lose some of that electricity, but now basically...
Wait, so at this point, is nothing going through the...
No, you have to have some flowing through it, or otherwise you wouldn't complete a circuit. So imagine this is like we've partially filled the dam, so we're still allowing some water to flow over the dam. We haven't completely shut off the flow of water through it, okay? So what's happening is that I've got some electricity flowing through every part of this. But when I open this up, okay, then Mother Nature says, I don't have another path. The only path that it can take is through that capacitor. And then it's going to fully charge that capacitor. It's going to build this up again.
Okay.
So now if I open this and close this, that light goes out, that voltage drops very rapidly. Got the idea. Now, if I put a second capacitor in here,
Oh, no.
okay?
That's complicated.
It's gonna be-
So, now,
In series?
we'll put it in series.
That means that it'll go, if you put more of
Or
those,
put it in
inverse, 1, 2, so it'll make it smaller.
Hold on.
What? No, not, what's the capacitance?
Hold on.
What is capacitance?
What, farads?
What is it?
Farad.
Capacitance, area
Okay.
over distance.
So now,
Farad.
I've got a second capacitor, right?
Yeah.
So, close this. Now, what happened to that capacitor?
The voltage?
The voltage.
The voltage. What happened to the voltage measured across that
It
capacitor?
went out, but not as high as it was before.
Why?
Because it's split between the two.
Yeah.
And there's less capacity.
Now it's like you have two dams and a river. Okay? So now I have two dams and a river. So each one's going to be holding. So now, because they're in series, how do you add capacitance?
Inverse.
Get the inverses of each other. Okay, so this would be like 1 over plus 1 over, and then you take the inverse of that. So by putting two capacitors in series, just like the resistors, okay, so if you put two resistors in parallel, okay, if you put two, think about this, go with what you know. If you have two resistors in parallel, what happens to the effective overall resistance?
Goes down.
It goes down, okay? If I put two capacitors in series,
Same thing.
Capacitance
same
goes
thing,
down.
because the effective overall capacitance goes down because you're adding the inverses of it.
Yeah.
Now,
Wait, what is capacitance
Fair
change?
Is that
so
like
now,
resistance for
I
you?
know.
what if I did this? Okay? So what would it look like to put this capacitor, what would I physically do to put this capacitor, let me get rid of some of this.
Yeah, I'm not gonna lie, I don't know the path. Of
Okay, yeah, we're gonna clean
Kinda
this thing
messy.
up a little bit. We're gonna make, this is the downfall of actually building circuits and wires. It's like, which way did it go? I don't know. Okay, so I've got, here's just gonna be one capacitor. Okay, we're gonna leave everything else out of it. Okay, boom, close the switch, lights up, boom, fully charged, across there, life's good. Okay,
Almost.
so now, what would it look like to put this capacitor in parallel with that?
You just twist the wires together and then plug it in.
I really don't want to twist the wires together. I've got a whole bunch of wires.
attach something on that little metal thing,
Attach something on this little metal thing.
and then put
That was,
another
that,
capacitor
was-
there.
that was the most,
Scientific,
yeah. Put something on,
I say twist the wires, that's my input. That's
Okay.
my professional opinion.
all right. So
What would
now,
twisting the wires do?
we'll put this,
This is parallel.
Oh,
okay? And then,
They look like fireworks.
watch out, Gracie.
what are firewoods?
What?
Like the capacitors.
They
said
do. They
light
look like
fireworks?
little M40.
Yeah, the M80. dude.
What's that?
Yeah, it's a
What's a firewood?
A
Fireworks.
firework?
Okay,
Come on.
so,
Fireworks.
now that they're in parallel, okay? So if you think of these electrons coming through here, they're gonna hit and they're gonna branch off.
Yeah.
Okay? So go up there, come down here, boom, we're back over here. So when I do this, okay, oddly enough, the same thing happens.
Yeah.
Lights up, but these are in parallel, so the capacitance actually
Decreases.
increases or decreases. In,
Yeah, increases.
because of the fact that
You just add it.
yes, because capacitors in parallel, you just add them together, right? So now, if I measure
Voltage.
the voltage,
Q delta V equals something.
okay,
It's gonna be
Yes, it
different.
does. Well, it's gonna be the
half.
same for one.
Delta
No,
V.
wait, will it be the same?
It'll be
Oh
the
yeah, it
same
will be
for
the same
one.
for
I need my equation.
ooh, now look what happens
It's
here.
K as one, not.
Way
But
high.
it'll be,
It's
So
the
notice-
A
same.
little big.
because it's for the both.
This is the same for both, because when it was in series, if you think of like of it being like a dam in a river, okay? It was just like this one, when it was in series, each one was holding like half. But now when they're in parallel, like that river split, and now it's going to fill up both dams equally. Louis,
If you, on the voltage meter, if you swap the yellow and the red ones, will it change the voltage?
it'll just, the only thing that would happen is it's just going to give a negative value.
No, I mean like since that is after this, wouldn't this just be reading one capacitor?
No, it's still going to, if you push this over here, it's still measuring that voltage across the capacitor. Because it's all basically, the electrons kind of view this as just one big connection.
Gotcha. So
Okay.
that's both capacitors in one voltage, right?
Yeah, so now if I move this over here, okay, and measure across, okay, which,
Wait, now
Wait,
what
a
would you do?
capacitor has like no, it doesn't change like
okay,
I see.
the
So
amps
now, so each
or
one
voltage or anything.
has the
right?
voltage of this battery.
It just
Now, what'd you say?
Will it like, what's a like a capacitor?
Overall,
It won't change anything except for stop the flow of the current, right? Like it
No.
won't change the resistance or the voltage or anything.
No, the only thing that happens is that over the period of time, okay, and this is why time is a factor. So initially,
A long time.
it's like it's not there. It's just like it's a wire. But as it builds up, then it stops it. So, but this is bleeding enough through that this is lighting up. In reality, it shouldn't. LED lights are very, very sensitive to electricity. If this had been like an incandescent bulb, this would be out. Okay, but it's allowing enough to go through. So it's the same idea though. So now if I take this,
You all shut up.
That's mean, bro.
Sorry, wait.
and hold on. And, okay. So now, when I hook this one up, now what's happening? It's the exact same idea. Now what's happening? It's avoiding all of these capacitors, and for the most part, and it's subverting that electricity out around it. Got it? Good? Okay, back we go.
Yes.
Turn V4 off. Hat trick.
The code word is hat trick. If you don't score a hat trick, then you're not allowed back in the classroom.
Yeah.
Isn't that right, Mr. Burkamp?
What's that?
If
Is
he
that
doesn't
it?
score a hat trick in his soccer game, then he's not allowed back in.
He's not allowed back in?
Yeah, can't go back in.
That's a little bit harsh, but
No, it's $10 for every
It's
hat
V4.
trick. Not
It's V4.
yeah.
okay.
What do you think?
All Brazilians are good at soccer.
That's how I love. They're born with it.
Wait, he's Brazilian?
Come on.
No, he's white.
Actually, I had no idea what his ethnicity
What did
was.
you say? What did you say?
I didn't say that.
Oh, that's crazy. That's crazy. That's crazy.
Hold on.
Is that crazy?
That's intense is what it is.
That's
It's
Intense.
I found him great, that was intense.
I'm disappointed.
What? What's this? What are you, my mom? Hot.
Wait, dude.
What?
Don't worry.
Ooh, that was a good one.
Tell me the truth.
Oh, that wasn't a good one. I don't think you can do it.
Oh, hold on, I drew that wrong.
Hot dog. Hot dog.
My uncle, I don't know why. Actually, no, I'm not gonna say that because that's weird.
You're gonna say something like that.
Good choice.
My uncle.
Never mind.
Yeah, my social talent is that I can actually
Yeah,
crack
no,
jokes.
I did like an intro.
Really?
Shut up.
That's tragic.
It was kind of an intro.
Sort of.
That's
Where's
actually
Connor
tragic.
today?
You have to do
Yeah,
it.
where's Connor? I forgot.
Couldn't tell you.
Connor is.
He's in the bathroom.
Connor's at home watching One Piece.
Watching what?
Really?
Hey, it's a TV show he's always watching.
It's an anime.
No, I have no idea what Connor is. He wasn't in football. Or
Maybe he's
first,
sick.
sorry.
He's skipping.
It's not even senior skip day.
It is for Connor.
Easter egg helpers. Yeah, I heard that one.
Easter egg helper.
For NHS.
Oh, is that your community service?
Oh, yes. Well, no. On Thursdays, we go do cats. Like,
They- Yeah,
like,
they do.
Go to cats.
like we
sounds-
volunteer with cats.
Oh, okay. In the kitchen?
Okay, so here's the story.
I got
So
that on camera.
let's say that a lot of times with capacitors, you want to look at like a ratio of different things. So let's say you have two different capacitors. One is 10 centimeters by 10 centimeters, okay, so about like yay, and separated by a distance of 4 millimeters, okay? So remember, millimeters is about like the thickness of your pinky. So you'd have, this situation, you'd have two plates, each one kind of about the size of my hand, 10 centimeters by 10 centimeters, so about like yay, separated by about 4 pinky nails separated across. Then the other one is, another capacitor is 5 centimeters by 5 centimeters, so half that dimension. But it's closer together, and that's separated by 1 millimeter. So what I want to figure out is what's the ratio of the capacitance of these two things.
Wait, what's the 5 centimeters?
That's 5 centimeters by 5 centimeters.
Oh, that's the area.
That's what we mean. So one's 10 by 10, the other one's 5 by 5.
Wait, I'm confused. Is that 10 centimeters by 10
Are those
centimeters?
separate
Yes.
capacitors?
Huh?
Are those separate capacitors?
Two completely separate capacitors. All I want to find is the ratio of the values of their capacitance.
1-1.
Okay, so one's 10 centimeters by 10 centimeters,
Yeah.
and the plates are separated by 4 millimeters.
Gotcha.
The other one is a smaller one, 5 by 5, but they're closer together, 1 millimeter. So what I'm trying to figure out is, I don't want the numeric value, I just want this ratio. Okay? Now, if you look at the units, Marilla, hand me your yellow sheet. So if you look at this epsilon naught, which is 8.55, yeah, 8.55 times 10 to the negative 12th coulombs squared over Newton meters squared, okay? So this is this epsilon naught. And like I said, technically, there's this K in front of it, don't worry about it, okay? So the whole point being is that this is just going to be a constant, okay? Same value. So if I want to find this ratio, so let's take C2 over C1, right? So that'd be epsilon naught, and then this area, if you really want to get picky, right? So if you really want to do this right, you'd convert those centimeters into meters, and you would have what?
Something meter square.
Yeah, so 10 centimeters is
0.1.
0.1 meters, right?
No, really, you got me.
Squared. True? Okay? True? Cool with this?
Yeah.
Then we're going to divide by that distance. 4 millimeters divided by 1,000 would be 0.4
meters.
meters. Okay? So if you wanted the actual value of that capacitance,
Divide.
you would take 8.55 times 10 to the negative 12th. Now let's look at this. This is 10 to the negative 12th, right? Pretty small number.
There.
You're going to take 0.1 and you're going to square that, which is even going to be a smaller decimal.
Even small.
And then you're going to divide by 0.004. Hey, that's going to make it go up a little bit because you're dividing by 10 to the negative 3rd.
Wait, how come you put no K?
Because
K
it's
is
one.
one.
Okay? That's what I
It
said.
is?
Okay.
Oh my god.
But why? It's 99.
Not what? What are you?
Where do you get 99 from?
No, that's a different K. That's from like.
So
A long time
it's
ago.
1.
You're talking about a spring concert.
Is it really?
My brother.
Are you just looking at the K on the sheet?
Which K?
It's the Greek letter cow, and it has a value of
Oh,
1.
you're looking at this K right here.
Oh, okay. K equals 1. Good to know. That would have been
Yeah,
bad.
where is that at 90?
I wish that was on me. I should have told you that at the beginning of this lecture.
Yeah, because honestly, I was like so busy.
He did.
I was busy writing them down.
Where'd you even get 99 from?
Yeah, where is that on
There
this?
is no
Where do you
99.
There's 9.
Oh, yeah, there is.
Oh, sorry. It's
Wow.
9, 10 to the 9th. I say 9E9. Sorry.
Oh.
Oh, yeah, okay,
sure.
that
Good
makes
save.
sense.
Good save. Good save.
You're talking about coulombs constant.
Yeah, that's what I was talking about.
Okay,
99.
that's like
Yeah, 9E9.
that's
It makes sense.
that's a Coulombic constant. This is a Greek letter K.
Okay.
Not-
Sorry, guys.
okay. Anyway, back to our story. So it's the Greek letter cow, and it's going to be 1. Okay, just go with that. So now we're going to divide that by the second one, which is going to be the same E naught, because all we're trying to find is the ratio. So do you even need to do we even have to worry about the E naught?
No.
No, because that's just going to cancel out anyway. So then I've got 5, which is going to be 0.05 meters, but that's going to get squared. And I divide that by 1 millimeter, which is going to be 0.001. So, somebody do the math.
1 to 1.
It's a 1-to-1
We
ratio.
didn't even have to why do you have to convert them? You don't even need to convert them.
Well, that's why I'm saying if you were really hardcore,
Yeah.
okay, if you actually had to find the value of the capacitance,
Then you have to do
you had to do that.
Yeah.
Okay, so that's why I wanted to point that out. So if I said, actually find the value of each capacitor,
Okay.
you would have to do that
For
conversion.
the ratio, you
But if all you're looking at is just a ratio, then it doesn't make any difference. Yeah, you could have left that as
100.
10 squared over 4, and then 5 squared over 1, which is 25 over 25,
Yeah.
it's the same ratio.
Yeah.
Okay, so if that's what I'm saying, if all you want is the ratio, as long as they're the same, centimeters and millimeters, same thing. But if you want to actually find the value, you have to do that conversion. Okay, let me see.
All done. Hot dog? All done. Hot dog?
Oh, it's a switch.
It's a,
I can't even see your eye.
it's a resistor.
Hopefully.
That's it.
Probably gonna be on a test.
Are you serious right now? Yes,
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 it is.
It is,
actually.
Sam.
You
What do you
can't see
mean
my
it
eyes,
is?
but it is actually.
Okay, so let's look at this. So you've got, so what's in that circuit?
A battery
A battery,
and a
capacitor, and a
resistor.
switch, and a
Resistor.
I
resistor.
thought it was that weird. I was like,
Okay? So I close the switch. What would the current versus time graph look like?
At the beginning, it would just be a line,
It's gonna be the
a
same-
straight horizontal until it
Same the
becomes
whole
fully
time.
charged, right?
Straight lines.
It's gonna go
Right?
down like this.
Depends if the switch is closed or not, really.
As I-
You just said the switch. You said the switch is closed. Oh my goodness. Oh, what's going on?
Sorry.
It's Monday.
He's in regret right now.
My bad, I didn't do that.
You caused an amount of
He's in regret.
That's his guilty voice.
That was funny.
Okay, Louis. I'm gonna close the switch,
Closed it.
which is what I said. Okay? I'm gonna close the switch.
Yeah.
Okay, the arrow makes it more obvious.
So what's gonna happen to the current versus time graph?
slowly go down.
Slowly.
Yes.
I thought you said
Yeah,
at the
over a
beginning
long
it
time.
stays.
So
it
at
just
when
acts
I
like a
first
current.
close it, is that gonna be maximum current or minimum?
Maximum.
current?
Maximum.
It's gonna plateau and then go straight to zero.
No, no.
What?
It slowly goes down.
It slowly goes
So as
down.
soon as I close that switch, that capacitor is gonna begin to build up,
Yeah.
right?
Yeah, so isn't it horizontal? I feel like it's horizontal.
No.
What? But you said it just acts like a current.
It's not slowly going
And it just goes through it.
Slowly going
It
down.
is, but that's what I'm saying. But as soon as you get a current through it, it's going to build up, and then it's going to, that current is gonna become smaller. It won't just go horizontal, boom, and then just drop off. Okay? So over the period of time.
So it does have an effect on the current?
Yes.
So
That's what
then,
this is, that's what this
No, it
graph
doesn't like
is
change
showing.
the overall amount. Of
but it
current.
doesn't change the overall amount of current flowing through the capacitor?
No, once that capacitor is fully charged, your current's gonna go to zero. There-
So where is it fully charged at? At the very back.
Once that current goes to zero is when that capacitor is fully charged.
Marla, there won't be a question on like in the middle of the capacitor charge.
So let me give you just what Sam said. It's either gonna be at the beginning, and the electron's gonna flow through, or I'm gonna tell you after a long period of time, what's gonna happen to the capacitor.
Are you gonna make us draw that?
Only thing I'm gonna expect you to know, Moreau, is that at the beginning, you have your maximum current. Over the
Okay.
period of time, that current is gonna go to zero.
Okay, I can do that.
That's the only thing I'm gonna expect you to know. Okay? It's the only thing I'm gonna expect you to know. Okay? Cool with that?
Yes.
Now, what would the voltage across the capacitor versus time look like?
Up. This way.
The same.
Up.
It stays the same.
Voltage?
Up.
Voltage of
What would the voltage across the capacitor versus time look like?
Across.
Sam, you're saying this.
What?
You're gonna go back
Of course
on.
it goes up.
Yeah.
No. This is just, I'm gonna close this. Don't worry about anything else hooked up to it.
Okay.
There's no external lights hooked up to this.
Okay.
All this is a voltage time graph. There's no lights Nothing.
Up.
But it's across the
I guess
So
up.
I'm just measuring the
Everyone's saying
voltage
up.
across that capacitor.
It's gonna
Start
steadily
at zero.
rise and
It's
plateau.
gonna start at
You
zero,
still have that there, like,
Rise
shut
and
up.
plateau.
Yeah.
Yep.
and then it's gonna increase, and then it's going to,
Plateau. Oh, it's
Flatten
like a
out.
rhythmic-
so
Okay,
when
see,
that
that's
current
the
goes to
plateauing. I
zero,
got
that's
that
when
part
that
right.
voltage flattens out. Okay? So what you're doing is that you're building up energy behind that. So if you look at Q equals C delta V, right? So clearly, as the voltage increases, what happens to the amount of charge on the capacitor? It increases. Okay?
Is the Q
So-
charge or energy?
Huh?
Is the Q charge or energy in this case?
Q is going to be charged here because that's going to be coulombs delta V.
Yeah.
So this
Okay.
is just the same equation as.
Yeah, the only
charge?
difference is there's just a half. Okay. Already went over
So
that, did that. Okay, so I am done.
capacitance is pretty much like constant for each capacitor itself, right? Yeah.
It's just an average hiccup, Sam. Leave it alone.
No, it's an average.
I
It's
wanted
not even
to see
cool.
if I could
Just average.
just see if I could replicate
It's a
it
mediocre hiccup.
accurately.
This is an
Not even an interesting.
I don't think up though.
Okay. So Cap, is this a long assignment?
No, it's not bad.
Be the
Can we see
person.
what it took you to do?
Can you put it on the Elmo so you can see?
Yeah, can we just like take a picture of your sheet? Actually, no, they didn't.
So this is all it took me to do.
Oh, okay.
So
I didn't even see that.
Depends if there's any short answer questions.
Depends on the
This-
short answer questions, it may take.
Now, but I'm going to tell you right now, the bulb problems are tricky.
The bolt?
Bulb,
Oh, gotcha.
bulb. And yes, you have to rank them in brightness.
Yes, sir.
Hey, what's the highest
one's the brightest?
One being the brightest.
One's
It's
the
just
brightest?
going to say, it'll tell you rank from dimmest to brightest or something like that. So
Vito
when in
told
doubt,
me to
put
do
in,
I'm right.
I'm gonna tell Vito to do the opposite.
Dimmest. To brightest.
I have a lot to do tonight.
Edit here. There's a wall right here.
No, thank goodness. My schedule's updated, so I only work 4 days a week now.
It's like, it's actually like a circle. It's
So
like
only Tuesdays,
dimmest
Wednesdays.
to
Thank
brightest.
goodness.
Others up there in intelligence.
Well, it's not too long. Can I have Sam? Yeah, Sam, you heard
What
me.
did you just say?
You heard me.
What did you say?
You heard me.
Hey, how many problems did you make on that? None?
Ooh.
Come back to me?
Tomorrow. I know.
Okay.
He gave you the answer.
He's running it up.
no, that's it.
He gave you the answer.
Oh, that's it?
Yeah.
So on these questions,
British.
uh,
There you go.
14 and 15, those are bulbs, okay? So if you want to, if you're not sure how that's going to play out, go to that FET simulation and build the circuit. Now, don't flip out when you get to number 14, because some kids just can't handle this. So if you look on 14, it's like a triangle like this.
Oh my goodness, what is that?
Stop.
It kind of looks like a
No.
flag.
Not a triangle.
Doesn't it look
Oh,
like
what
the
the-
Puerto
Oh
Rican
my
flag?
god.
Does it? I was thinking
Oh God, what is that?
another one.
What's the other flag?
So
African one? One of the Africans?
So with this one, and don't flip out and go, oh my God, it's a triangle.
Oh my god, it's triangle.
This is bad. We've never seen triangles before. We've only seen right angles. It's in series, okay?
But C and AB are in parallel, right?
I'm just telling you, just don't get hung up on the triangle and go, it's different, okay? So just,
Did you just say
These,
different?
these, the light bulb, right?
Did you just
That's
say
a light bulb?
Yeah,
yeah, those are all light
this is
bulbs.
random though.
What page is this on?
Whatever the end of chapter 23 is.
Yikes.
Yeah, sit back down.
I'll find it.
You will attract athlete. what I thought.
Oh, right,
Track athlete.
Here, I'll tell you.
Who's a track athlete?
How'd your track meet go, Pop?
What?
How'd your track meet go?
Absolutely horrible.
Oh.
Okay.
It was, well, the wind, it was like 50 mile per hour wind gusts, so that.
Did you go to Emporia?
Yeah. It was really awful. Half our team has dropped out.
Really?
Page 754, Morella.
Oh. 754?
Page 750.
Thank you very much.
Alright.
Okay, is that all?
That's all.
Bye, Vitor.